Ugh, why is it so hot in here? Why does it feel like we're in a heat wave? Oh, look at them! It looks like they aren't bothered with the heat. No, my friend, it's not because they don't bother with the heat, Whew. But rather because they don't feel the heat. Do you want to know on how to make your house more cooler? Not that kind of cool. This kind of cool. I know that the Philippines only have two seasons, the dry and the wet season, in which almost half the year the Philippines mostly experience drought and hot weathers due to climate change and global warming. Scientists predict that future changes are expected to include warmer atmospheres, a warmer and more acidic ocean with higher sea levels and larger change in precipitation patterns. The extent of the future climate change depend on what we do now to reduce greenhouse gas emissions. So we need to make our houses more cooler for us people to naturally live in extreme weathers. How do you ask? Well, did you know that these little guys are responsible for making buildings more cooler inside rather than out? Hi, my name is Lifedwimbel G. Samala, and I will be teaching you what hydroceramics are. These are called hydrogels, three-dimensional networks of cross-linked polymers that have been heavily saturated with water. When hydrogels are mixed into concrete, they can release the water they have stored to accelerate the curing process. This results in less volumetric shrinkage and cracking, extending the service life of the concrete. Because the hydrogels retain moisture, necrotic and infected tissues can be deprived painlessly, gradually encouraged, and full healing is encouraged. They are suitable for wounds with high to moderate exudation because they have high water contact and are not totally absorbent. These are hydrogels are then used for constructing hydroceramic that is placed for cement in creating buildings. When hydrogels are mixed into concrete, they can release the water they have stored to accelerate the curing process. The Hydroceramic project seeks to understand how hydrogels materials can be used to passively address thermodynamic processing in buildings. These materials include hydroceramic cement. It is also monolithic solid composed of concentrated NaOH solution and methacholine. It is created by hydrothermally curing a combination of inorganic waste, calcined clay, vermiculite, Na2S, and NaOH with the water. Hydroceramic. Hydrogel is a polymer which expands in water 400 times of its volume. Hydrogel is 98% water, so it evaporates it. It cools down the surroundings. As it losing water, it gets smaller and turned back to the original solid state. Composite material. Hydroceramics is a composite materials that benefits for the low evaporation property of hydrogels. When integrated into ceramic, as the water evaporates out, the ceramic absorbs the water and passes coolness to the surroundings. Material components. Interior ceramic layer. Convex design pushes the hydrogels out and increases the cooling surface area. This causes the stretchable plus absorbent fabric spreading water and allowing the expansion of hydrogels. In the exterior ceramic layer, it holds and folds, holding the hydrogels in place. Evaporation cools down the surroundings in combination with ceramics, porosity, and hydroceramic performance as cooling systems to the buildings. These are some examples of the fabrication processes that the hydrogels occurs. It is then baked at the 1000 degrees Celsius. It is then tested in performative prototype versus the control group. Here you could see the different types of methods that the scientists use to measure or to test out if the hydroceramic gels are capable for the process of hydroceramic. As you could see, manufacturers also measure the humidity and temperature of the hydrogels. If the hydrogels are then graphed to differentiate whether if the hydrogels are compatible when it comes to construction use. Moving on how engineers and scientists use the benefits of hydrogels. Hydroceramic can take the place of air conditioning, which lowers the temperature inside by 5 degrees Celsius. Due to the hydrogel's capability to absorb water up to several times its weight, temperature can be lowered. Researchers have found that the shape and chemistry of hydrogarnet crystals form at a high temperature, about 200 degrees to 350 degrees Celsius, in cement-based hydroceramic materials with additions of alumina and silica. The hydrothermal CaSH or CaO, Al2O3, SiO2, and H2O. This is the chemical formula for hydroceramics. This system includes these minerals. The predominant aluminum carrying phase that forms in hydrogarnets or Ca3Cl2 SiO4 to YOH4Y, and the addition of silica has a lesser effect on its composition than the curing temperature. X-ray diffraction or XRD data have been found using the Rietveld method to determine the composition parameter Y. Minor elements including Fe, Mg, and S are present in the hydrogarnets according to the electroprobe microanalysis or EMPA. The hydrogarnet composition infrared from XRD was validated by EMPMA data. It is seen in both octahedral and octahedral forms. Higher minor elements concentration is linked to the isotetrahedration shape. In simpler terms, when the powder components are mixed with water, hydrogen reaction occurs. The hydraulic calcium compounds react with water to form the calcium silica hydrate or CSH, the calcium aluminum hydrate products. Other calcium aluminum hydrate phase like CH and CaSH can also form. The composition depends on the powder components and the activators used. These additional binders phase enhances strength and durability. Hydroceramics also contribute to the goal of the passive cooling technique, is to reduce the summertime surface temperature and make cities feel colder. The engineers created a porous ceramic passive evaporation cooling wall or PECW with a high capacity to absorb water for the cooling effect to work. Here are some advantages and disadvantages of using hydroceramic cement. Let us all first go on to the advantages of hydroceramics. Number 1 is low thermal conductivity. Hydroceramic cement has a very low thermal conductivity, making it useful for insulating applications. This helps reduce heat transfer and energy costs. Number 2, it resists to high temperatures. It maintains its strength and integrity even when exposed to very high temperatures over 1000 Celsius. This makes it suitable for applications like fireplace insulation. Number 3, resistant to moisture and water. The hydroceramic cement is water resistant and does not degrade easily in damp environments. This durability makes it good for outdoor applications. Chemical resistance. It is resistant degradation and corrosion from exposure to acids, alkalines, and many other chemicals. This allows it to use hazardous chemical environments. And lastly, low density. Hydroceramic cement is a lightweight with a porous structure. This results in light construction and reduced structural loads. Here are now the disadvantages of using hydroceramics. Number 1, brittle with low tensile strength. While strong in compression, hydroceramic cement has a relatively low tensile and flexural strength when it comes to prone to cracking and breaking. Number 2, shrinkage during drying. Considerable shrinkage while the material is drying can lead to cracking unless properly accounted for. Third, difficult to shape and install. Hydroceramic products may be friable and break if not handled correctly during shipment and installation. Care is needed to be taken. And lastly, high cost. Compared to traditional cement, hydroceramic cement tends to have a higher cost due to specialized production methods required. This can limit applications. There are actually other benefits of using hydroceramic cement other than the cooling a building. Number 1 is high strength and durability. Hydroceramic cement can achieve high compressive strength, even higher than Portland cement concrete. The dense microstructure also provides excellent durability and abrasion resistance. Number 2, low shrinkage. The cement exhibits very low drying shrinkage, reducing cracking compared to Portland cement systems. This is due to the chemical shrinkage being completed in the early stages of the curing process. Number 3, chemical resistance. The cement matrix provides resistance to acids, sulfates, and other harsh chemicals environment due to its low permeability and high alkalinity for solution. This makes it suitable for applications like nuclear waste contaminant and chemical uses. Number 4, low thermal conductivity. Heat transfer is restricted across hardened hydroceramic cement, making it effective insulations. This helps maintain desired temperatures within buildings or other structures. Number 5, rapid setting. Hydroceramic cement can be formulated to set and gain strength rapidly. Unlike slower setting Portland cement concretes, this enables quicker construction turnaround times. And lastly, number 6, environmentally friendly. Since the cements utilize industrial byproducts like fly ash and slag, they can reduce the CO2 emission associated with a typical Portland cement production. That's all for today, and thank you for coming by. See you next time!